All right, welcome to part 5 of the power simulation tutorial series. In this video, I'm going to show you how we can add an electrical component to our model that we used in the last video. So now we're starting to get into an entirely electromechanical system now. So if you want to grab the model from the last video, you can go ahead and go to the GitHub to grab that. I also have the 6-wheel model put in there. So last time I said I would make a model of a better representation of what the Rover would actually be like. So it's with the 6 legs of the suspension, so all 12 wheels in action, moving the Rover. So if you want to use that and play around with it, go ahead and grab that too. For now, I'm just going to stick with the one-wheel model, just that way it doesn't take me time to copy and paste everything into 6 different legs. Right, so if you wanted to grab the already finished model for part 5, you can go ahead and grab that too and just kind of look over it as I go through the video. All right, so I'm going to go over to our wheel model that we have set up. So last time we set up our rover body. So now we actually have a physical model of our rover moving along terrain with the headwind and possible incline. And we also have our tire that is parameterized with traction and normal forces and inertia and everything like that. And then we've also got our drivetrain here, so our gearboxes that step up the torque, and then our torque sensor, or our torque source, which up until now is what we have been using as our DC motor. So I'm actually going to show you how you can implement a real DC motor into your model. So what I'm going to do is I'm going to actually delete all of this here, and I'm actually going to disconnect this as well. I'm just going to drag these guys off to the side for now. And I'm going to search up DC motor. So DC motor. This is from the Simscape electrical library. So before we were just using driveline, now we actually need to start using electrical. So go ahead and download that library if you haven't already. I believe I showed you how to do that in video 3 actually, sorry, video 3. Okay, so now we're going to take this motor, and this R port is our output. So we're going to feed that into our S port on the gearbox. So this is working the same way as our torque source in terms of connections. So we have our C port connect up to the rotational reference, and our R port hook up to our gearbox. And now this is basically our transition from an electrical system to a mechanical system. So it's going to take electrical power and convert it into mechanical power just like a regular DC motor does. So the first thing you want to do is after you add in your DC motor block, you are going to want to initialize the variables inside. So open up the parameters block, and this is how we are going to specify the characteristics of our DC motor. So the DC motor that they have set up already is, based on the looks of it, it seems like a pretty weak DC motor, probably something that kind of like a hobby motor. What we're using for the Rover is a bag motor. It's quite big and it's pretty powerful. So we're going to have to change these parameters for sure because this will not move our Rover. So what we're going to do first is we're actually going to change this. We're going to set this up to by stall torque and no load speed. So all of the parameters that I have figured out, I actually did empirical tests on this block in a separate model during my development stage. And I used the torque curve from the bag motor and the data sheet to try and get as close of a representation as I could get. So I'm just going to put in the parameters that I found out from that test. If I've got time later on, I might make an extra video and show you how I did that, so that if you wanted to take your own motor that's slightly different than ours, then you could actually figure out the parameters to be putting in here. So the next thing I'm also going to change is change the rotor damping. So I'm going to go by no load current. And I'm basically going to make variables for all of these again. So I'm going to go into MATLAB here, and I'm going to set up another section in our edit vars script for all of the electrical constants that we'll be using, or electrical variables and constants. So the first thing I'm going to set up is our inductance. So inductance, this is going to be the inductance of the rotor. And I found that worked best if I set it to 12 e to the negative 10 henries. And then next thing I'm going to set up is stall torque. So from the data sheet of the motor we were using, our stall torque is 0.43 newton meters. And then the no load speed, I'm going to set that up as 1,000 or 13,180 RPM. And then we are going to do the, actually I have to change the name of this, that is not right. No load speed. Okay, that was really bad. You cannot name your variables like that. Okay, and next we are going to do rated voltage. So rated volt equals 12. That's the rated voltage for the motor. Then we're going to do no load current, which is 0.8 amps. And then no load voltage, which is also just 12. So I guess I can just keep that as rated voltage when I put in the parameters. And then we're also going to do the inertia. So rotor inertia. And this is one of the variables that I had to play around during testing. So the inductance and the rotor inertia are kind of arbitrary values that, well, not exactly arbitrary. They were tested empirically, and I found that these ones worked best, gave me the best output. But the stall torque, no load speed, rated voltage, no load current, I got those all from the data sheet and the torque curve. Okay, so now I'm going to save this. I'm going to run the script just to load those in, and then we're going to go into back into our parameter block here. So armature inductance, actually I'm going to bring up this just to make sure I'm just going to spell everything right. Okay, so armature inductance, we call that inductance. Use that variable. Stall torque, called stall torque. RPM, or the no load speed, and always make sure that you've got the right units on this side. You can change them, just make sure that you have the right ones, or else it's going to give you very weird values. Rated voltage, and down here was our no load current, and this was also rated voltage, just because they're both 12 volts. And we're going to go to the mechanical section, and we're going to define our rotor inertia. So rotor inertia. All right, perfect. So now we have everything set up for the motor. So the motor is now very close to being what we have actually set up for our rover. But the next thing we have to add in is our HBridge. So this is something I had to kind of test out myself and just make some assumptions about our controllers. The controllers that we have for the rover right now are just off-the-shelf components that we didn't make in-house. So we're not exactly sure how they work. We know how to control them, we just don't know what the internals do really. So right now we're just using the HBridge. That's your typical method of controlling a DC motor, is using the HBridge. So now what we have to do is set up a electrical reference. So setting up a ground. So type in electrical reference. This is now the ground for our circuit. So you have to connect all of the components that are grounded to this line. So connect the DC motor's ground. We're also going to connect this import and this import. So for our purposes, this is the brake and reverse imports. You would normally send a signal there if you wanted to brake or reverse the HBridge. but we don't want to do that in our simulation. If you want to be ambitious and actually go into like reverse and stuff, then that's cool. You just have to get that hooked up properly. Um, yeah, so it's not too difficult to do. But for our use, we're just going to hook that all up to ground. And now we have to move our solver to connect it to the electrical ground. Okay, so now we're going to go into our HBridge. We have a few things that we have to set up in here. So we have a couple different simulation modes here. We have something called PWM and averaged. Basically what PWM does is it actually sends like a serious PWM signal through the lines. So a signal that jumps between high and low based on the duty cycle and has like a frequency that's defined. In our case, we're going to use the averaged mode. This just makes it a lot smoother for our calculations, has a lot less computational requirements by our simulation, so it's going to run faster. So the averaged mode is basically what the HBridge would be seeing in terms of equivalent voltage from a PWM. So a PWM signal that's started at 5 volts running at a duty cycle of 1 will be a 5-volt signal in averaged. But if the duty cycle was 0.5, so half your regular duty cycle, then like a 50% duty cycle, sorry, then you would be running at about 2.5 volts running out of this HBridge. Sorry, running into the HBridge. So you're using the equivalent voltages of PWM and duty cycle rather than the actual signal that jumps between high and low. And then the next thing we're going to do is go into input voltages, enable threshold voltage. That's just with the signal that goes into the PWM port here. As long as it's above this voltage, it's going to register and actually like turn on the HBridge. But what we are going to do here is we're going to set this to PWM volt and divide by 2. We're going to set this to PWM volt. This is the PWM voltage that we're actually going to be using. These other ones we're actually also going to set to PWM volt 2. Not that we're using them, just good practice to set them to half the PWM voltage. Now that we have those variables set up, we need a PWM voltage. So PWM volt, set that up to 5 volts. It can be anything, like you can have it running at 5 or like 1.8 or 3.3, whatever your PWM voltage is for your, like, I guess if you're running something like this, it could be microcontroller, it could be like, I don't know if you've got your own PWM generator on your Rover, but typically it's going to be a microcontroller. So let's just say our microcontroller has a PWM voltage of 5 volts. I'm just going to set that up and then save our changes. Now we are going to go into here and yep, that's all set up now. So these are going to be 2.5 thresholds. And going to go into the bridge parameters. So this is very important that we get this to match the rated voltage of our DC motor. So when the HBridge is receiving a PWM voltage of 5 volts, then it's going to output 12 volts. If it's receiving a PWM voltage of about 2.5, then it's going to output about 6 volts. So it's just going to scale based on the input that you're getting it. So then down here, we're going to change total bridge resistance. This is another thing that I had to test out. The number that I found that worked out well for our motor was 1 e to the negative 6. And the other 2 parameters here we can just leave as is. So set that okay. And now we're going to go back to our model here. So now we have an HBridge that controls our PWM, or it controls our DC motor by changing the voltage that's applied over the poles of the motor. So at 100% duty cycle, we're going to be getting 12 volts across here. 50%, we're going to be getting 6 volts, as I said earlier. So higher duty cycle, more speed. yeah, and like initially, well, not more speed, it's initially more torque, and then you'll get up to more speed. Um, but now what we need is something to control our HBridge. So you need some sort of equivalent to the microcontroller that you would be using. So what I'm going to add in now is a oh, controlled PWM voltage. So this is basically going to be our PWM source from a microcontroller. I'm just going to connect this to common ground here. Okay, so you need to connect the reference, all reference points to the same ground, and PWM needs to connect into, or output needs to go to the PWM import. So it's going to send a PWM signal across this line. So now we're going to go into this block, and we are going to set up our PWM frequency. So in this case, we're going to set this to 4,000. That's just the frequency of how we are going to be running our motor. What our microcontrollers are capable of and what we decided we wanted to run it at. And we also have to change the simulation mode here to averaged to match the HBridge. So both of them have to be running on the same mode. If you want to be using PWM, that's fine. Just make sure that both of them are set up for PWM. Input scaling. So what we're going to do is at these reference inputs and output, or these input points, reference 0 is going to connect to ground. So I'll actually just do that real quick. Reference plus is going to take an input voltage, and then it's going to send out a duty cycle on the PWM based on the input voltage that it gets. So in our case, let's say we want to set up our input voltage to be the exact same as the average voltage of the PWM at 100% duty cycle. So in that case, we're going to have PWM volts, that's 5 volts. So what's going to happen is if we feed 5 volts into this reference point, it's going to send out a PWM signal of duty cycle 100. And because it's on average mode, it's going to send in basically a 5 volt source. If we changed our reference input to 2.5, we're going to get 2.5 on this end. You can't actually hook up a voltage source directly to PWM here. You do need a PWM controller like this, even if you're on average mode. So just make sure you still have this. Very important. And then our output voltage, we're going to change this to PWM volt as well. So this will be the amplitude of our PWM signal. And set that to OK. Now the next thing we need is some sort of source that we are able to control so that we can send in a voltage to this reference point. So I'm going to add in PS sensor into our model. I'm going to hook this up here, connect the negative to the ground and positive to reference. Now basically what this is it can be a variable voltage, variable current, or variable resistor source. So you just send a physical signal, PS signal, into this import, and then it will send out the exact same source on the outside. So you can either set up a gain, an offset, whatever you need. In our case, what we're wanting to do is send in a signal of the voltage we want and actually have it output the voltage that we are specifying. So in this case, our sensor gain is just going to be 1, because if we want to send in a PS signal saying 5 volts, then we want this signal or this source to actually provide 5 volts. So we don't want to change this, and because we're dealing with voltage, we're going to keep this on variable voltage. Okay, so now that we have that set up, we need to get our PS signal. So we'll connect this up here. So this is our PS, or Simulink to PS converter. So now we can send in a Simulink signal to control our entire model here. So we're going to control the voltage, which then controls the HBridge and the DC motor, which then pushes the rover. So what I actually want now is I want to be able to specify the duty cycle that we are sending through our microcontroller as an input to the system. So I want to see what happens when I change our input duty cycle, how that affects the movement of the rover. So what I'm going to do here is I'm going to make a gain block. Now this gain block, I'm going to set to PWM volt. Okay, and going to just expand that so you can actually see what it says. And I'm going to just insert it right here. So now our step input is basically going to be our duty cycle. So if we have a step input of 1, that's going to correspond to a 100% duty cycle. So it's going to get multiplied by our PWM volt, which is 5, feed that into our source. So we're going to supply 5 volts. Our PWM source is going to get 5 volts, so it's going to give 100% duty cycle, and then you know the rest. So we're going to change our step input, and we're actually going to name it duty cycle, just so that we remember what it is. And just remember we need to change this too. So let's actually set up some new variables. So we're going to call this one duty initial, and we're going to call this duty final. We're just going to go specify that in our edit vars as well. So duty initial, I'm going to set that to 0, and then duty final, let's set this to 0.5. So that's like a 50% duty cycle now. All right, so we're going to save our changes, and then we are going to open up our model again, and we should be able to run this and see the output. VM, okay, maybe I made a mistake in the HBridge. I'm gonna debug this and be right back. Okay, so I just found that I called this rate volt and not rated volt, so that should fix our problems now. So let's run this. Duty initial does not exist. Did I spell it wrong? All right, let's just check in here. It's there. So maybe I spelled it differently in here. Yeah, I think that's what it was. Duty initial. Okay. Okay, let's try this again. Hopefully no errors this time. Doesn't seem like it. Okay. All right, so there is the output, and this is the speed of our rover. See, as it's coming out of the V out port. So from 0 to 2, our speed is 0. Actually, do I have a headwind set up? Because it's not perfectly 0. I do have a headwind. Okay, so I have a headwind of 1 right now, which is not a very heavy wind, but it is enough that you can see that the rover is, let's see where my position 1 reader is. It's moving backwards at about, or it is moving at like micrometers per second. Really, that's just 0. It's only not saying 0 because it's got that headwind against it. But anyways, that doesn't really matter. So as we can see at step input 2, or at time equals 2, our step input is then put up to a 50% duty cycle. So we can see our rover start to speed up. And because we are now controlling it with duty cycle, our DC motor is then specified to a specific torque based on the input duty cycle that's given. And it will eventually max out at a certain speed. So as you can see here, like that certain speed is somewhere around 0.6 meters per second. So if we were to change, say, the final duty cycle, and let's say we would change this to 1. So we're going to do a step input from a 0 duty cycle to 100% duty cycle. Let's just see what that looks like when we run the model. Oh, right, we haven't, we need to edit the variables. That would fix that. And actually, let's just set this stop time. We're going to change that to 10, just so that you have time to see, because it does need time for the rover to actually speed up. So you'll actually be able to see where it speeds up and uh, levels out. Okay, there we go. So it's maxing out around 1.36 meters per second. So that's good. That is a good speed for us to be maxing out at. You can also check out how fast it's accelerating by measuring the slope here. So we're just going to take 2 points. You can see the slope is around 1 meter per second squared. So that's a pretty fast acceleration. But typically you wouldn't be running a motor starting at 0 to and then jumping up to like 100% duty cycle, just because something else that I'm going to show you is the current draw from something like this. So another thing that you have to be careful of when making a rover is that you don't want your current to be exceeding the maximum current that the rover can supply, that your batteries can supply, and you want to know how much power it's going to be taking to run your motor as well. So what we'll want to do is actually measure the current and measure the voltage being supplied to the DC motor, so that we can figure out the power that's being consumed, the electrical power that's being consumed by the motor. But before we do that, I actually want to make a subsystem. Just to make this a little bit cleaner and easier to see, I'm going to take all this, and just like I did in the first video, I'm going to right click and create subsystem from section. So in here, okay, we do not want these outputs. I don't know what created those. So just get rid of these signals here. Okay, so now we have an input, which will be our duty cycle. Do need to name that so it's easier to see. But now our entire system is in one block. So you can get our duty cycle and our scope here, and it's a lot easier to see. So this output, we're going to name the signal velocity. And we're going to change this so that it goes by the signal name. And we're going to change this input to duty cycle. And also change this to be the signal name. Okay, so we'll call our subsystem Mars Rover. So now we are feeding a duty cycle in. So this is like taking our software and setting an instruction for a specific duty cycle to be sent in from our microcontroller, and it goes into the rover, and then we can see it moving at a certain speed. So the next thing I want to do is I'm going to take all of this and I'm going to shift it over, because I want to add in a current sensor and a voltage sensor. So I'm going to set up current sensor, and just like a regular ammeter, you have to connect this before the load and in series for it to give a proper reading. And then this output is going to send out a physical signal. So we're going to need a PS to Simulink converter, and put that right here. Next thing we need is a voltmeter, so voltage sensor. And now we are going to place this in here. And just like a regular voltmeter, you have to place it in parallel across the load. So connect up the positive to the positive, negative to the negative. And we're also getting another PS signal coming out here. So we need PS to Simulink converter. And connect these up. And I'm actually going to move this up here. It's going to be a little messy, but it'll make it a little bit easier to see. So now what we have is we have our voltage and our current coming out here. I do want the current to be outputted as a variable so I can see what that looks like. So I'm going to create an output port output, and I'm going to connect that, let's say up here. And we're going to call this, I'll call this current. Name this after the signal name. So as you can see, now we have another port called current. But I'm not done yet. I want to set up another port for power. So let's do output. And actually, we haven't named it yet. So basically, to get power, for electrical power, what you do is you multiply voltage with current. So what we need to do is set up a product block, and we are going to multiply the current with the voltage. Move this over here, connect these up, and then connect current, and connect voltage. And I'm just going to name this voltage. And this output signal we will call power. And we'll change this to be the signal name. Okay, so what's happening here is we're reading in, oh, I have those mixed up. Okay, this is current. This is voltage. Sorry about that, voltage. And we're going to disconnect this, a pretty easy fix. And then we're going to connect that here. Oh, connect this here. And we're going to go by signal name, which should update to current. Not sure why it's not updating to current, so I'm just going to delete it, put another one. Oops. Output. Connect it here. Oh, come on. Okay, and signal name. Okay, there we go. Now we have the proper current. So we are measuring the current, and we're measuring the voltage, and we are outputting the current. Then we're going to multiply the current by the voltage to get power, and then we're going to output the power. So on this end, I'm going to create another scope. And this scope is going to take the current, and let's do power as well, just so we can see what it looks like. All right, so we are still at 100% duty cycle, so I'm going to show you why you don't want to go from 0 to 100% duty cycle. So I'm going to run the simulation. So just remember, as we saw before, this was the velocity of the rover. You can see it started to max out. Starts to speed up at 2, and it starts to max out around 4 seconds. So now we're going to take a look at the electrical output. So as you can see here, this yellow line, I'm just going to bring up the measure. This yellow line is our power consumption. So right at 2 seconds, you can see it goes up really high, and it's actually really hard to hit, but it's peaking out above 600 watts of power, which is pretty crazy power consumption for like just an inburst of power consumption. And then you can see it starts to come back down, it starts to average out, and then hits another little peak, and then starts to flat out around 4 seconds, just like the velocity. So once the rover is starting to get into a constant velocity, then the current and the power consumption are all starting to balance out into like a steady state there. So I'm also going to go to current, switch over to current, and this blue line is our current consumption. So you can see here that we go up, and we're hitting, looking like around 43 amps, which doesn't seem too bad, but that is only one motor. So eventually when we have 6 motors working at the same time, taking the same duty cycle, because we are going in the same direction, same speed, that is going to be 43 times 6 amps, which that's going to be pretty close to 300 amps, which is ridiculous and way over what we can provide on our Rover. Um, so now that we know this, we know that we can't actually operate going from 0% duty cycle to 100%, but that's fine. Um, I'll show you in the next video how you can control the input duty cycle and kind of make like an entire trip simulated by different input cycles. But yeah, so that's about it for this video. I just kind of showed you how you could implement an electrical circuit. It is a pretty long video, sorry about that. But it is really important stuff to cover because this is kind of like um, the most important part of our simulation is seeing how our power and current consumption goes. Um, so yeah, so if you want to grab the model from the GitHub, again, I'm going to update the six wheel model to also have all these inputs so you can see um, what a fully decked out rover looks like in terms of power consumption and velocity and stuff. So I will add that in and let you see that. If you want to grab that. Otherwise, in the next video, I will show you how to actually create custom signals and actually simulate like a full trip of the rover.